So for this video, we are going to do 5 questions to consolidate the idea and concept that we have learned. So question 1, let G be a graph where it has 21 edges and n vertices. Nk is a notation for the number of vertices of degree k. So there are 3 degree 4 vertices and the rest of the vertices are of degree 2. So you have only degree 2 or degree 4 vertices. If that is the case, what is the value of n? The sum of the degree is equal to, since it has 3 degree 4 vertices, so from here is 3 times 4. And from here it is n minus 3 times 2. Summation of the degrees is actually equal to 2 of the sides. We can cancel each of the term by 2. 6 plus n minus 3 equals to 21. So n will be equal to 18. So 18 is the answer for question 1. Very simple question. So this is question 2. It's a little bit tricky. Let G be a k regular connected graph with 24 edges. Find the sum of all possible values of the order. Meaning that find the sum of all possible values of the number of vertices of G. So this is 48 is less than 7 squared. So which means that k is not more than 6. Then we can just list out all the possibility. If k equals to 1, then n is equal to 48. If k equals to 2, n equals to 24. K equals to 3, it is equal to 16. And k equals to 4, it will be equal to 12. It cannot be equal to 5. K equals to 6. Then this is equal to 8. So are we going to add up all these values of n? Now we have to wait for a while and think through it. Why is it so? Because yes, it is now k regular. However, it has to be connected. Now imagine that for this option, it's a 1 regular graph on 48 vertices. 1 regular graph on 48 vertices, it will be something like this. No matter how you draw it, it cannot be connected. So therefore, we have to rule out this option, right? How about for the rest? For the rest, it is possible to be a connected graph. So we will accept the rest of the n, and the sum will be equal to 1, 2, 3, 4, 5, 6. The sum is equal to 60. So 60 is answer for question 2. Now this is question 3. Let G be a graph where G has 21 edges and the maximum degree of G is equal to 5. 5 to 1. It is a good number. It's a prime number. Now, given this condition, what is the minimum value of the order of G? So this question is quite similar to what we have already discussed last time. Recall that we have this inequality. Average is in between the minimum and maximum. So now we are going to use this part of the inequality. From here, Vg will be greater than or equal to 2Eg over maximum of G. And that is 2 times 21 over 5. This is 42, this is 84. Vg is greater than or equal to 8.4. Since this is an integer, and the order has to be greater than or equal to 9. Now we have to think through whether 9 is possible. So we can construct a graph with all of the vertices except one is of degree 5. It is not difficult to construct such graph. And therefore, we confirm that 9 is achievable, and therefore 9 is the answer for question 3. So this is question 4. Let G be a graph on 12 vertices. Find the minimum value of the number of edges so that G is always connected. The key point here is G has to be always connected. G is on 12 vertices. Let's say we are lucky enough and we have only just enough, let's say 11 edges. Then the graph may be connected by doing this way. And the graph may be connected, and this is one of the example. Later on, we will learn that this is defined as a tree. Tree is a connected graph that do not consist of any cycle. We do not want to base on luck. What is the minimum value of G so that G is always connected? Suppose G is not connected and we have two components where this is 11 vertices and this is one vertex. If G has 50 edges, then I will make all the 50 edges go into this component. Since this component has 11 vertices, then the number of vertices that it can absorb is 11 choose 2. 11 choose 2 is equals to 55. If the number of edges is less than 55, we can always put it into this component, and the resulting graph is not connected. So in order to make it connected, then the minimum value of EG should be equals to, the minimum should be equals to 55 plus 1. So when you have 55 edges, I put here, then there will be extra edges that force me to join into here. And therefore, the answer in this case is 56. So 56 is the answer for question 4. Okay, this is question 5. Let G be a graph on 10 vertices. The maximum degree of G is equal to 8. And the distance for any two edges is not more than 2. Find the minimum value of the number of edges of G. Since the maximum degree of G is equal to 8, there exists a vertex U such that the degree is equal to 8. 1, 2, 3, 4, 5, 6, 7, 8. Here we already have 9 vertices, and G is a graph on 10 vertices. Let's say this is a V here. Since the maximum degree is equal to 8, U and V are not adjacent. So we left with the connection here. In order to make the distance of any two vertices is not more than 2, one of the possible way is we just join V to any of these vertices. Or we may change a little bit in this way. The distance of these two vertices is 1, and the distance of these two vertices is 2. For any two vertices, it still fulfill the condition that distance is not more than 2. So for this graph, it has 16 edges. So naturally, we want to ask, is 16 the minimum value? In order to see that, now we just consider, without this vertex U, what will happen? This is V, and you have 8 vertices here. In this subgraph G minus U, we note that V has to adjacent to at least one of this. Suppose not, then when you go back to the original graph, V is not joining to any of these. It will mean that V is an isolated vertex, and therefore the degree cannot be less than or equal to 2. So suppose it joins to this vertex here. The distance of V to any vertices here has to be at least 1 or 2. In other words, the graph G minus U has to be connected. If G minus U is connected on 9 vertices, then you need at least 8 edges. Then when you come back to this, 8 plus 8 is equal to 16. And therefore, 16 is the answer for question 5.